This means that fully fault-tolerant quantum computation is beyond the reach of the current technology. This situation motivates the search for approaches that give us information and knowledge in order to act at the level of hardware design, and also to tailor, say, the error correcting schemes in order to reduce the overhead. And in this context, non-Markovian noise is a type of noise that is particularly unfavorable for the following reason. First of all, by definition, it depends on the history. It can accumulate, it does not reset, and for this, it can give rise to strange patterns. Secondly, we know that currently schemes designed to address non-Markovian error are less established than ones for memoryless error. For instance, we know that randomized benchmarking has become the golden standard to verify noise in quantum circuits. However, this is based on the Markovian assumption, so assuming that the noise is Markovian and essentially identically distributed. By less established, I mean that currently the scheme for non-Markovian error delivers worse error thresholds than one for memoryless error. A natural question would be, then when is non-Markovian present in our setting? And the answer is that this is basically ubiquitous. So it's present in any real-world setting or setup for quantum hardware and experiment, whenever our quantum system is coupled with the environment, which acts as a memory for us. So a more suitable question would be, when is the Markov assumption? So the Markov assumption means that we can neglect the non-Markovian effects. When is this assumption particularly bad? And the answer is that when our system is strongly coupled, so coherently coupled with the environment, or to another system we cannot control or we don't have access to. Examples for these are, for instance, two-level system defects in superconducted circuits, which yield non-Markovian noise effects, and also nuclear magnetic resonance, where essentially the atoms we are investigating may be strongly and coherently coupled with another system, other atoms. And so again, non-Markovian effects will arise. There is, however, a wide range of schemes to evaluate non-Markovian noise, looking at different perspectives. Here, I have highlighted two of the most prominent methods. One is the divisibility criterion, where essentially we check if a quantum channel can be written as a composition of the channel itself from two different times. So from T0 to T1 and to T1 to T, where essentially T1 is an intermediate time. And we want to check if this stands for all possible choices. Another way is to look at violation of monotonicity for different quantities like quantum correlation, decoherence, quantum entropy measure, channel capacities, and so on. But there is even more. So there are approaches to look at the information flow between the system and the environment. There are geometrical criteria like looking at the variation of the volume of quantum states. There are methods based on the recent progresses in the field of machine learning and deep neural network, and there is even more. However, these schemes suffer from a number of shortcomings. This can be, for instance, that some of them may need a complete knowledge of the master equation. I will explain in a few minutes what I mean by master equation, or a characterization of the system-environment interaction, or again, some assumption of the underlying dynamics. So basically, this means that to use these methods, one needs either some knowledge, partial knowledge, or some assumption on the setting you are investigating. Some of them also act only on qualitative level, so they do not provide a quantitative description of the non-Markovian dynamics. And the method like the divisibility criterion constitute only one-sided witnesses of Markovianity. So they can signal non-Markovianity, but essentially a witness disappears for Markovian dynamics, but also may disappear for some non-Markovian dynamics. So they are not suited to capture all instances of non-Markovian noise. We will see how we try to lift or at least mitigate some of these shortcomings with our novel approach. But first, let me just refresh in 2 minutes the concept of Markovian process. First, the classical case, and then we do one step further and we look at the quantum case. So a Markovian process is one whose next step, future steps, only depends on the current state and not on the whole history. Mathematically, for instance, a classical and discrete time Markovian process, this is expressed as follows. So the Markov property means that the value acquired by a future variable only depends on the last one, so on the current one, and not on all variables in the history. We can also go continuous time, and then we look for what is arguably one of the most renowned stochastic Markov processes, which is Brownian motion. Here we can define the filtration function that keeps tracks of the continuous time stochastic process of its history. But yet the Brownian motion, so a future variable, depends only on the current state, on the current value of the variable, and not on the whole filtration, so not on the history. In the quantum case, instead, a quantum Markov process is described by a one-parameter semigroup. This means, again, that we can write the channel as a composition of the channel itself for 2 different times, S and T, where essentially we divide the total time for 2 intermediate times T and S. And this, if you think about it, embeds the idea of memoryless, because essentially the evolution from time S to time T plus S, you see that only depends on the value acquired at time S, and not what happened between 0 and S. So this embeds the idea of memoryless. But for a quantum process, we also need an additional condition, which is that the process must give rise to a sequence of completely positive and trade-preserving channels, so proper quantum channels. All right, so these 2 properties define what a quantum Markov process is. However, this is equivalent, and I stress the word equivalent because it is exactly a necessary and sufficient condition, is equivalent to writing our quantum Markov process with a generator, essentially, that must satisfy the following equation, Lindblad master equation that we see here. So we have first a unitary evolution part, so H is the Hamiltonian, and the second part is a dissipative part that expresses the interaction between system and environment, and is characterized by the so-called jump operator J alpha. We then call a generator satisfying this equation a Lindbladian, and indeed this is the most general description for a quantum Markov process. The question, a natural question that can come is that given a quantum channel, is it consistent with Markovian dynamics? Or in other words, does a Lindbladian exist such that the channel can be written as being generated by this Lindbladian? This is a well-known but also well-investigated question. Is it called the Markovian problem? Some of you may know it as the quantum embedding problem. And this has been shown by Toby and collaborators to be NP-hard in the system dimension, but efficient in the required precision. By required precision, I mean how closely you want to approximate your quantum map with a Markovian evolution. And this will be exactly the approach we will take for our method. So we will have as an input a tomographic snapshot of the quantum channel. So at some time we pick a tomographic snapshot, and we ask whether this is consistent with a Lindbladian evolution. So if there is a Lindbladian that can describe the quantum channel, so the tomographic snapshot. We can even extend this method by taking multiple snapshots for different times. And this, of course, gives a significantly more sensitive test for Markovianity, because essentially we require the Lindbladian generator and the evolution to fit all data point, tomographic data points. So it's a stronger test for Markovianity. In words, so
ask a question
to give you more details.
Emilio, there's a question.
Yes.
So in this definition, a time local like Lindblad equation with some time-dependent coefficient is not considered a Markovian like channel, right?
No, it's not. The tomographic snapshot, we don't know whether this is Markovian or not. We want to see
the generator, like in your previous slide, and one before that. Yeah. So this L, if it has some time dependent in H or J's, that wouldn't be considered. The resulting evolution wouldn't be considered Markovian in this definition. Is that correct?
What we work on time independent generator. So our generator is supposed to be time independent. However, the method, so the Lindbladian equation also holds for time dependent Lindbladian. But then, of course, we have to essentially correct the approach. But the approach can be still extended to continuous time time dependent Lindbladian. But yes, for our setting, we only consider a time independent case.
Okay, thanks.
And this will give rise to a proper Markovian evolution. But yes, as we will discuss, one of our outlook is indeed to go to a time-dependent Lindbladian. For the moment, is time independent. And indeed, our approach is then to see how we can fit. More precisely, given as an input a few tomographic snapshots, our goal is to retrieve the Lindbladian that best approximate the dynamics of these snapshots within some given precision. And if we don't find a Lindbladian that approximate the snapshots, alternatively, we want to measure the non-Markovian component in terms of white noise addition. I will later define this measure, which is not a unique measure for non-Markovianity, but a well-defined one, and one that also is sensible for different settings. And we do all of this by casting a convex optimization task, whose constraints are exactly the necessary and sufficient conditions for an Lindbladian generator that we will see in a few minutes.
Another question, Mohammed?
Yes.
So I have a question. In the quantum channel, the time is implicit. So there is no time. This 1 to Q, is it like some time stamp that you enforce your system such that they correspond to the specific times? And if so, what's the origin of time? Because now I have a non-Markovian process. So what is there is some arbitrariness in defining what time is? What like is that given to us? Like,
of course. So essentially, we can take our snapshot at any time, and we just need to record the time of the initial evolution. So we are not bound to what was the initial let's say the initial time. Is just a relative time with respect to starting the process itself. When we use only a single tomographic snapshot, we don't even need to know at what time this was taken, because essentially you can rescale your Lindbladian by a scalar variable, which is the time, and still satisfies all constraints of our convex optimization. So we need to record the time only when we take the different snapshots, and these are, so to speak, relative times, because essentially you don't need really to know when the process started.
thanks.
All right, and by using the convex optimization, this conveniently allows us to include an error tolerance parameter that essentially allow us to handle with tomographic inaccuracies. And this means that the method is robust with respect to state preparation and measurement errors. And moreover, we inherit from the Toby and collaborator result the fact that our method for fixed Hilbert spaces is efficient in this required precision. Moreover, we have additional advantages. One is that we don't need any a priori knowledge of the master equation, nor any information about the system and the interaction between the system and the environment. So we can run our scheme completely blindly. Moreover, it's also arguably low resource demanding, because all we need is just a few tomographic snapshots. A single one would already suffice. And finally, the method is quantitative. So we provide a full description of the Lindbladian, approximating the dynamics, or as I said, in alternative way, a quantitative measure of non-Markovianity. And I would say that altogether, this property makes the scheme interesting and valid for a number of instances. Before illustrating the core algorithm, I need to define the mathematical framework. This is a bit more than just some mathematical preliminaries, because our method essentially is just bringing together these different mathematical notions. So we need to define channel representations, condition for the Lindbladian generator that we use for the last point as constraints of the convex optimization program. We've also defined the measure of non-Markovianity in terms of white noise, and technically what is the matrix logarithm and the corresponding branches. But first of all, let us define some notation. We will use the bracket notation with EJ being the natural basis. We denote the maximal entangled state by omega, and by omega perpendicular, the projection onto the orthogonal complement. Finally, by F, we denote the flip operator interchanging the copies of the natural basis of two Hilbert systems. So, as we are dealing with quantum channels, we want a way to represent them as matrices. And we will make use of two representations. The first one is called the natural basis representation, which essentially means representing the quantum channel in the natural basis entries. This is the natural basis representation. We can do this for channel, but also on density operator or matrices the channel is acting upon. So we can then express a matrix as a vector in the following way. We also override one definition. So we override the definition of Hermitian adjoint. We say that the Hermitian adjoint of a vector is given by taking the complex conjugate and then apply the flip operator. You may ask why we do this, and the answer is that taking the Hermitian adjoint in this way of a vector corresponds to taking the conventional Hermitian adjoint of the matrix the vector is representing. So we are just translating the Hermitian adjoint for matrices into the vector representation. And very conveniently, in this representation, concatenation of channel is just a matrix-matrix multiplication, and a channel acting on a matrix is a vector matrix multiplication. So this is our first way to represent channels. The second way is called the well-known Choi representation, where essentially we pick our channel, we couple it with the identity channel acting on a Hilbert space of the same dimension, and then apply this to the maximally entangled state. The Choi representation is very useful to investigate the hermiticity preserving property. This is a very important property for us, so please keep this in mind. Indeed, this means that essentially a channel is hermiticity preserving when this commutes with the adjoint operator, the conventional one, for all input matrices, as you can see here. And indeed, we have that a channel is hermiticity preserving exactly when the Choi representation is Hermitian. And so this is our second method to represent channel. And very conveniently, the two representations are directly related by a mapping called the gamma involution, which acts on the bracket notation of natural bases in the following way. So is simply permuting the second and the third entry, as you can see here. And indeed, under this involution, the two representations are directly related. All right, now is an important moment because we are going to define necessary and sufficient conditions for an Lindbladian generator. So one that gives rise to a Markovian process. There are three conditions. So the first one is what we already mentioned, is the hermiticity preserving condition. The second one is called the conditionally completely positive conditions. This means that essentially we are taking the Choi representation. So we start by the natural basis. Then with the gamma involution, we have the Choi representation. We project it onto the complement of the maximally entangled state, and we check whether this is positive semi-definite. And these conditions ensures that the generator will give rise to completely positive channels at any time. Instead, the trace preserving condition is given by the left action of the maximal entangled state, giving rise to the zero vector. For practical reason, and I really mean practical reason, so when implementing the algorithm in Python, it's convenient to express the three conditions in the Choi representation. Because essentially the second one, as you can see, is basically already in Choi representation. And the other two becomes as follows. As we have seen, a channel that is hermeticity preserving means that its Choi representation is Hermitian. The second condition is essentially unchanged. And the third condition becomes that the partial trace on the Choi representation is zero in any matrix norm. And this will be the condition we will leverage in order to cast our convex optimization task. I also would like to remark that this condition implies a very rigid eigenvalue and eigenvector structure for Lindbladian. So,
sorry, real quick, one more question.
Yes, please.
So this partial trace, what is it with respect to? Like, what's...
Partial trace is essentially taking the partial trace of the first half of the system. And then this should be give rise to the zero matrix, which is equivalent to say the matrix is zero in any matrix norm. So essentially, you are only taking away half of the system, so the first half. This is a condition you derive.
But this half is, yeah, I guess I was confused about like this concept of half of the system. Is it because you're now taking this, you're doubling the system size to go to this representation? So the first half is really...
essentially, you can, since the Choi representation somehow is coupling the system with a system of the same dimension.
Okay.
So essentially, you give rise to a system of the double dimension, and then you trace out the first part.
Okay, thanks.
It's the same thing if you have a channel and you want to check that it's trace preserving, you trace the same part out.
Only in the choice, but this is true when you pick the choice. So when
in the choice, the same trace one for the channel in the Choi matrix form as well, right?
Yeah.
Okay.
And all right, and these are very important conditions. Please keep them in mind because we will see them in a few minutes. I was just saying that indeed this implies a very rigid structure for the Lindbladian because I have three remarks. One is that if a complex eigenvalue lambda, a complex number lambda is an eigenvalue of the Lindbladian, then also its complex conjugate is an eigenvalue, and moreover with the same multiplicity. Secondly, we know that if an eigenspace of a complex eigenvalue must admit a set of basis vectors whose Hermitian conjugates span the eigenspace of its complex conjugated pair. And by Hermitian conjugates, I mean the Hermitian conjugates we have defined before. Instead, if lambda is real, then the eigenspace must necessarily admit a set of basis vectors which are either self-adjoint or coming Hermitian-related pairs. So essentially, there is a very rigid structure for both eigenvalues and eigenvectors that we are going to exploit in the last part of my contribution when talking about perturbation of operators having a degenerate spectrum. But first, let us also define our measure of non-Markovianity in terms of white noise addition, or you can also say isotropic noise, or a depolarizing channel. It is not, as I mentioned, a unique measure for non-Markovianity. There are several measures, but this is well defined and also is reasonable in a number of settings. So, in few words, the concept is that is the minimum amount of depolarizing noise to be added to a generator of a channel to make it Markovian. So mathematically, this means that is the minimum value mu in order to make the generator conditionally completely positive by adding the second part, which is expressed the isotropic noise. And what I would like to highlight is that adding isotropic noise will only affect the second condition, so the conditionally completely positive condition. It won't alter the first and the third one. So you cannot, for instance, make a channel hermeticity preserving by adding white noise. All right, and this will be our alternative measure for non-Markovianity when we cannot retrieve a value in Lindbladian. We also need to define a technical tool, which is the matrix logarithm. So assuming we have some matrix having all different and non-degenerate eigenvalues. Let us also denote the left and right eigenvectors by L and R. Then we know that the zero branch of the matrix is uniquely defined and well-defined in the following way, by taking the logarithm and coupling with the one-dimensional subspace, the logarithm of the eigenvalue. However, as in the complex number case, we know that there are infinitely many logarithms. So essentially, by
Is it just me or have we lost Emilio?
No, it's also me.
Same here.
Yeah,
Feel probably-
I think Emilio's back now.
Oh, he's
sorry,
back?
line?
Yeah, you're back. You got to share screen again, though.
Oh, sorry. I resume right away, sorry. Does it work?
Yeah, you're on the right slide.
All right, sorry. All right, so we have infinitely many matrix logarithms by adding a 2 pi I phase to any possible eigenvalue. And this gives rise to an infinite number of branches that we label by this vector m, taking integer values. All right, and this is our matrix logarithm and the branches thereof. The final technical tool will be the convex optimization program, which is given a set of convex functions. We want to minimize over x, f0, subject to constraints as an upper bound for the other convex function. We can, in addition, have also constraints of this form. And the convex optimization task is very convenient because of the following property, that every local minimum is a global minimum. So let us see the right-hand side of this slide. So this is not a convex optimization task, because depending on the starting point, we may achieve a local minimum and a global minimum. And we cannot distinguish which one it is unless we run multiple times the task. So this is problematic because we don't know whether we have achieved the global minimum, so the optimal global solution. Instead, but unfortunately, the convex optimization will always look like this. So when we achieve a minimum, an optimal value, we have guaranteed that is the global minimum. All right, so this is the convex optimization task in few words, very, very synthetic. And now we have all ingredients in order to illustrate our core algorithm. So the algorithm at the core of our scheme. As I said, as an input, we will have a single snapshot, and we want to see if there is a Lindbladian that can approximate this snapshot. More precisely, we pick M as the tomographic snapshot, some real number epsilon, which expresses the precision, and an integer m max, which is essentially where we cut our search for the different matrix logarithms, because as we have seen, there are infinitely many, but we run our search over the vector m max, essentially, for our matrix logarithm. The output will be the Lindbladian.
Sorry, I have a question related to my first question. If I have a single snapshot, what does it mean to have the Lindbladian? Because if it's a single snapshot, I can take log of m, and then that would be my Lindbladian, and I define my t to be 1. It only makes sense if I have multiple snapshots that are time-stamped. So could you please?
Sure. What I see is that if I pick the logarithm of a matrix, it is not ensured to satisfy the three conditions we have just defined before. So it won't be a proper Lindbladian. So it won't give rise to a Lindbladian evolution, that generator. So the logarithm of a matrix is not automatically a Lindbladian. It can be seen as a generator, but not as a Lindbladian generator.
I think Mohammed's question is then, say if you do have a Lindbladian by picking the right branch, then how do you guarantee that the resulting Lindbladians at each time step give you the same Lindbladian times the time?
I don't know if I really understand this question. So if you have a proper Lindbladian, so a proper Markovian evolution, and you pick the logarithm, of course, if you essentially, you may say, all right, this will be a Lindbladian only if you pick a certain branch, right? And
Okay.
maybe you are not checking that branch. All right, in that case, we will fail. However, we have some heuristic to say that we need only small numbers for n max. So Tamara will address this question. Essentially, we can have a low value for n max, and in most cases, we will correctly check if we have retrieved an Lindbladian or not.
Okay, so say you did that twice at 2 different times, then you'll get a Lindbladian in each case. Let's say you succeed, L1 and L0. Yeah. How do you know that L0 is equal to L1 up to some scalar multiple that's the time?
Because if we have multiple snapshots, we try to generate this by the same Lindbladian for 2 different times that we record. So the condition that this will be the DERT algorithm is that we want to approximate all snapshots with the same Lindbladian. So find a Lindbladian that for different times approximate the different snapshots.
And your algorithm at each time snapshot is guaranteed to give you a unique Lindbladian? Because what if, how do I know you won't get another one that's not that one?
Because the condition, the assumption we do is that the matrix has non-degenerate spectrum. And in this case, the generator will be unique, and also the Lindbladian will be unique. So there is only one Lindbladian that, of course, there can be also multiple Lindbladian that can approximate the different snapshots, even though it seems pretty complicated, but we are not ruling out this. What we want to check if there is at least one Lindbladian that approximates the evolution and retrieve the one that best fits the snapshots.
Mohammed?
Yeah, maybe we should move on and
we
can discuss this towards the end again.
All right. So indeed, our outcome will be the Lindbladian that closely approximate the logarithm of the snapshot. And as a condition, we want this to be within the precision epsilon that we give. So the algorithm works as follows. We take the 0 branch of the logarithm. And then for every logarithm branch up to n max, we cast the convex optimization program on the variable x that we constrained to be a valid Lindbladian. So essentially, these are the constraints in the Choi representation. And what we want to do is to minimize the distance of the Lindbladian with respect to some branch of the logarithm of the channel. And if we find such a Lindbladian within the precision, then we apply the involution, we get our Lindbladian in the natural basis representation, and we output it in our algorithm. However, if we don't retrieve a valid Lindbladian within the epsilon neighborhood, so that we defined as an input, we cast a second algorithm, this time to retrieve the smallest Markovianity measure for a generator within the epsilon precision for the matrix n. So we want to check what is the smallest non-Markovianity measure for all channels within the epsilon ball of n. It works similarly. So we take the matrix logarithm, and then here we have to initialize an additional parameter delta that essentially expresses the precision epsilon in the matrix logarithm space. Unfortunately, it's not possible to have a one-to-one relation between the two quantities. So it's not possible to ascertain perfectly what delta is given epsilon. We are only given non-tight lower and upper bound. So what we do is start with the lower bound and then increase the value of delta until we achieve some upper bound. And this may give rise to some issues that Tamara will address in his contribution with a numerical example. For the moment, let us just initialize delta as expressing epsilon in the logarithm space. Then we do again the same. So for each logarithm up to m max, we cast a convex optimization, this time on variable mu and x, where mu is what we want to minimize. X is a Hermitian hermiticity preserving and trace preserving channel, indeed, that also becomes conditionally completely positive, so a valid Lindbladian, thanks to the white noise addition of mu. And moreover, we have the additional constraint that we want the generator and the map to be within the epsilon ball of the tomographic snapshots. The output will then be an hermiticity and trace preserving channel within epsilon with the smallest non-Markovianity measure mu. As I said, we can even extend our approach for multiple snapshots. So for multiple times, we pick a snapshot of the channel. And then we want to see if there is a Lindbladian that approximate all data points. So in this case, we have multiple snapshots as an input. We also have the times as an additional input, and then again, epsilon and then max that works as before. The output will be a single Lindbladian, minimizing this total distance. Maybe this explanation will help a bit about the question I received before. So we want the Lindbladian, minimizing this total distance with respect to the different logarithms, but also such that it approximates the generated Markovian channel, approximate each snapshot, each of these snapshots within epsilon. So it works again the same. So we take the zero branch for every logarithm. We define delta again as before. And then for each n branch up to n max of each snapshot, we cast again the convex optimization on the variable x with the Lindbladian constraint on the char representation, where we want again, as I said, to minimize this total distance with respect to the generator. And also with the constraint that every generated channel is within the epsilon ball. And as I said, this is expressed by the delta parameter in the matrix logarithm space. And output will be then the Lindbladian that indeed approximates those snapshots within epsilon. All right, so this concludes the explanation of our core algorithm. I still have a last part I would like to discuss. How much minutes do we have left, if I may ask, Victor?
Yeah, you're basically around 40 minutes now.
Oh, already 40 minutes. All right. In that case, I will just run very quickly through everything, this part. So the major complication of our approach is that we are channels having been the perturbation of an ideal channel with a degenerate spectrum. And this is a very, let's say, pretty often occurrence, since, for instance, every unitary channel has an eigenvalue 1, which is degenerate. So essentially, the problem is the following. If we have an hermiticity preserving operator, as we have seen before, this has a very rigid structure, both for the eigenvalues and the eigenvectors, which must be Hermitian related. A perturbation will then essentially give rise to a cluster of eigenvalues. So the eigenvalue with multiplicity will split. And same for the, as we say, also the complex conjugate must be an eigenvalue, and also it will split. But this is somehow well conditioned. So we assume that our snapshot comes from an ideal hermiticity preserving channel plus some perturbation. So as I say, the eigenvalues are well conditioned, but the eigenvectors may be ill-conditioned in the sense that the nice hermiticity preserving structure will be completely broken. And I had an example for this, essentially, that whenever the perturbation breaks the hermiticity preserving structure, our algorithm will fail. So I will skip this part. Instead, when the perturbation preserves the hermiticity preserving structure for the vectors, our algorithm will succeed. So our strategy to deal with hermiticity preserving operator that are perturbed will be the following. So the scenario will be that if we take directly the logarithm of a perturbed channel, which is originally degenerate, having the degenerate spectrum and hermiticity preserving, we take directly the logarithm, we cast the convex optimization. Then what happens is that the closest Lindbladian is one that sets the eigenvalue to 0, and not one that restores the hermiticity preserving structure for the eigenvectors and the eigenspace. So our algorithm will fail. But instead, what we do, our strategy will be the following. Will be to detect a cluster around some value lambda. So we want to detect something of this kind. So a perturbation, that means that originally there was an eigenvalue with multiplicity. The second step will be to detect a partner cluster, so the complex conjugate, and then retrieve a set of hermiticity preserving vector. So essentially restoring the hermiticity preserving structure of the eigenspace of this cluster. This will be our pre-processing phase for the convex optimization that we carry out for every cluster. Since this set is there is an infinite choice of vectors allowing restoring the hermiticity preserving structure, we will randomly sample from this set. And we do this many times. And Tamara will discuss what happens by increasing or reducing the number of samples. She will show the picture of how algorithm essentially evolves with respect to the number of samples. And then what we do, the idea is that we use these hermiticity preserving vectors as new eigenvectors of the snapshot. So we substitute the old eigenvectors, so the original eigenvectors of M for the cluster of eigenvalues with an hermiticity preserving basis of vectors. This will be generating a new operator R that we insert in as we pick then the matrix logarithm, and then by casting the convex optimization, we get a channel whose generated quantum channel is close to the snapshot. So the key idea is to detect cluster of eigenvalues that come from the perturbation of a possibly multidimensional eigenspace, restore the hermiticity preserving subspace and structure for this cluster, and inject it in the convex optimization. So this will be the strategy that I also discussed a bit in words, but conceptually is what I just said. And finally, this will be my last comment. The question is that if this strategy is always well justified. And the answer will be yes. So it is always justified to search for such an hermiticity preserving basis of vectors. And this justified that we will go for a structured search instead of a brute force unstructured search for the algorithm eigenvectors will give rise, which will make our algorithm fail. And essentially, this convenient fact is backed up by our main theoretical theorem, where we show that indeed the hermiticity preserving structure is stable with respect to perturbation in the following sense. If we have a channel which is hermiticity preserving and an eigenvalue lambda that is n-degenerate, then there always exists a basis of vectors spanning the invariant subspace of the perturbed version of the channel with respect to the generated cluster of this multidimensional eigenspace, and a set of vectors spanning the invariant subspace of the partner cluster, such that they are almost up to some error emission related. And so our search is justified. What I want to say is that given time constraints, in any case, I wouldn't be able to explain how this theorem works, so the derivation, but there is a lot of interesting and beautiful math concealed under this theorem. So if you are interested, I'm happy to discuss later. But now I think it would be very interesting to see some examples. Tamara will go through them and benchmark our approach. And with this, I thank you very much for your attention. Thank you.
Oh, sorry, I need to unmute, sorry. So yeah, as Emilio said, I'm going to talk briefly about the implementation and some of the results we've got. So obviously what we'd really like to do with this code is run it on real data and real devices, and we're hoping to do that later this year. But before we get to that stage, we wanted to run the code on simulated data to check a few things. So there are a few parameters in the code which we can't necessarily get a handle on what they should be set at analytically. So in order to determine kind of what to set those parameters as, we needed to look at simulated data. So this includes the branching numbers of the matrix logarithm, how many random samples we need when looking at perturbed degenerate eigenvalues, and also an issue to do with interpolating between distance measures in different spaces. So those are kind of the parameters we wanted to get a handle on. And also we just wanted to check how do our simulated results compare to analytical results when we're kind of looking at channels where we know what result we expect to get. So the first issue we looked at is the branching number. So in both our algorithms, what we do is run a very kind of naive brute force search over branches of the matrix logarithm. As Emilio said, there's countably infinite such branches, and obviously we can't search over all of them. It is known theoretically that there is setting m max to be doubly exponential in the dimension of the channel is sufficient. So if Lindbladian exists, you'll always find it by setting m max to this value. But obviously doing a brute force search over this many branches isn't going to be feasible. If you did want to search up to the maximum, there is actually an efficient algorithm that can do that. But although it's kind of theoretically efficient, in practice, it's not easy to run. And actually what we found is that you don't need to take m max to anywhere near this kind of value. Taking m max very small, even just 1 or 2, will in most cases find a Lindbladian if one exists. So there is some justification for this by physical arguments. So if you consider that setting m max higher, you're including more high energy components of the noise, and you kind of often don't expect those to play an important role. But the physical arguments are a little bit hand wavy. I think the better argument for not having to include these higher values is the numerical arguments. So what we've got here is the branching number numerics. So this is for what the two graphs show is the distance between the tomographic result that we got from simulated data and the Markovian channel that was found by our first algorithm for two 1-qubit Markovian channels. So on the left, we've got the X channel, and on the right, we've got the depolarizing channel. And there are two things to kind of note from these graphs. The first is that there's no kind of steady downward trend. As you increase the number of branches you search over, you don't find that the error in the code monotonically decreases, as you would expect if increasing the branching number gave you a better result. In both cases, there is some fluctuation. It's not just a constant result, but that's to be expected because these are both degenerate channels, so the algorithm is randomized, so we wouldn't expect to get the same result for every time we run the code. The other thing to note is that in both cases, for low values of the branching parameter, we get a error from the code that's of the same order of magnitude as the tomographic error. So the difference between the tomographic result and the actual ideal channel that we know we implemented. So this, along with, there's also been some work done on looking at completely random channels and looking at how increasing branching number affects the results there. And they back up the same idea that we don't need to look at high numbers of the branching parameter in order to get to find the Lindbladian. And so that's why we do a brute force search over just a small number of branches in all our other simulations. So the other parameter we wanted to investigate, how large do you have to take this parameter to get good results, is the random samples. So as Emilio said, if when we're pre-processing our channel, we detect clusters of eigenvalues, which suggests that our input is some perturbation of a degenerate channel, then we use a randomized algorithm to search over the set of possible basis vectors. There's infinitely many such possible basis vectors. And again, obviously we can't search over all of them. So we have to look at how many do you have to search over. So in Emilio's code, it's kind of this is the bit we're looking at, how many is many times here to get a good result. So we looked at this for some 1 and 2 qubit degenerate channels. So on this side, we've got the 1 qubit channels that we looked at. So again, it's the X channel and the depolarizing channel. And what you see again on the y-axis is the difference between the Markovian channel we found and the tomographic result. And on the x-axis, we've just got the number of random samples. This is if we, each of these is an independent run of the algorithm, which is why there's some fluctuation and where you don't always just see the error decreasing as you take more random samples. But there is a kind of a consistent downward trend, as you would expect. Taking more random samples tends to give you a better result. we found in the case of the X channel, above around 2,000 random samples, we're consistently getting a error from the code, which is on the same order of magnitude as a tomographic error. And 2,000 random samples takes around 10 minutes to run on just a standard laptop with no parallelization, no optimization. So it's a very kind of feasible runtime, and it could easily be optimized to make that runtime significantly lower. In the case of depolarizing channel, we found that the results are even better. Even with just 40 random samples, you're consistently getting an error from the code that's the same order of magnitude as a tomographic error. We don't fully understand why you need so many fewer samples for the depolarizing channel than you do from the X channel. We have some ideas, but investigating this further and trying to understand the topology of these Lindbladians and why the direction of perturbation seems to matter more for the X channel than the depolarizing channel is something we are interested in looking at. We've also done some 2-qubit numerics. I'll kind of skim over these because we're running low on time. But again, we found that even with 2-qubit degenerate channels, where obviously the code takes longer to run, it's still feasible on just a desktop computer to get good results. So the final parameter that we wanted to investigate where we need to set it is to do with interpolating between distance measures. So as Emilio said, in our algorithms, we take as input an error tolerance parameter. So the tomographic error we think we've picked up in our input matrix. But we have to convert that to a tolerance in spaces of matrix logarithms, because that's where we do all our convex optimization. There are results in the continuity of the matrix logarithm which justify this approach. And in the case of the first algorithm, where we're trying to find the Lindbladian, we don't have to be careful about anything. We just minimize delta and convert this to, and then convert it to epsilon and check that we're within the error tolerance parameter. But we need to be a bit more careful when we're finding the measure of non-Markovianity. And the reason for that is in this convex optimization program, we're not trying to minimize delta, we're trying to minimize mu, given that delta is less than some value. And the results from the continuity of the matrix logarithm don't give us tight upper and lower bounds for delta. So in this algorithm here, where we say, this distance must be less than some delta, we don't know exactly what that delta is. And the way we get around this is by interpolating between the upper and lower bounds of delta from the continuity of the matrix logarithm results. This doesn't, sorry, yeah, Andrew.
Oh, sorry, I didn't want to interrupt, but I guess I just wanted to ask, so you use the Frobenius norm in the distance between the Lindbladian and the channel. I was wondering if, I guess, what are the reasons for that choice, and also if you normalize it so that doesn't depend on the system size, or I guess D in this case?
No, we don't normalize it because we're just we're just looking to in the first algorithm we're just minimizing it, so the normalization doesn't really come into play. And again, in the second algorithm, we're just keeping it lower than delta. So kind of think of normalizing delta rather than normalizing the Frobenius norm. The reason we picked the Frobenius norm is because the convex optimization works well with the Frobenius norm. And also it has nice kind of operational interpretations in terms of the distinguishability. But yeah, it was more because the convex optimization works well.
Yeah. Sounds
yes. So the parameter we're interested in here is looking at this delta step. And we do have a little example of why that's important, but I'll probably skip over that because we're a bit low on time. But just that we can construct examples where if you set delta step too large, this algorithm fails, even though there does exist a non-Markovianity parameter. And we found that with some numerical examples. So what we can show here is a graph of the non-Markovianity parameter against the error tolerance parameter. And obviously, as we increase the error tolerance, we expect the non-Markovianity parameter to decrease. But what we found is that for certain values of the error tolerance parameter, if we set delta step too large, we don't find any non-Markovianity parameter, even though one does exist. So in this graph, a non-Markovianity parameter of 1,000 means we didn't find we didn't get any result from that algorithm. But we can always solve that by decreasing the delta step in our algorithm. Finally, we want to talk very briefly about benchmarking the results. So I won't dwell on this slide, we've kind of seen these results, but just to benchmark the first algorithm, we tested it on known 1 and 2 qubit Markovian channels in Cirq. And we found that with reasonable runtimes with kind of no optimization for runtimes, you can still get very good results where the error from the code is of the same order of magnitude as a tomographic error. Benchmarking the second algorithm is a little bit more interesting. So to benchmark the second algorithm, what we did is we took a known 1 qubit non-Markovian channel, which had a very simple spectrum. So in particular, it had no degenerate eigenvalues and no complex eigenvalues. The fact that it was 1 qubit and so had such a simple spectrum allowed for analytical calculation of mu, which we carried out in Mathematica. So the results from this are shown on the left-hand side of the screen. And then on the right-hand side, show the results from the convex optimization. So the graphs again showing the mu against the error tolerance parameter. And again, as you'd expect, as we increase the error tolerance parameter, we find that mu decreases. But more interestingly, we found that if we set epsilon to the value we got from the analytical results, then we get the same mu to within 3 decimal places. Cool, so just to finish up with the conclusions. So we've developed novel methods and algorithms to determine the best fit Lindbladian to tomographic data. And we found the simulated results are, we're getting very, very good results. This Lindbladian is very close to the actual, the Markovian channel is very close to the tomographic data. Our methods are completely assumption-free on the input channel and require no prior knowledge about the system-environment interaction. In the case of non-Markovian dynamics, we find operationally meaningful measure of non-Markovianity, where again we've benchmarked this with analytical results and found good agreement. In future work, we may consider whether we can generalize this method to incomplete tomographic snapshots, because that's kind of the big resource requirement in this method, is actually carrying out the process tomography. So can we lower that requirement a bit? The paper's on the archive and all the code's available online as well in this Git repository. So yeah, thank you for your time.
Thank you.